Right, so welcome everybody to our monthly Q&A seminar. Today we have the pleasure to have Professor Richard Layfield as our speaker. So let me introduce him briefly. I mean, he has a very impressive CV, so I had to select a bit of information about him. So he studied in England, in Leeds, first as a master's student, and then he moved to Cambridge for his PhD, where he graduated in 2002. And then he stayed in Cambridge first as a junior research fellow, and then as a lecturer. And then he moved to Manchester, where he progressed through his career from lecturer to reader, and then becoming professor. And then in 2018, he moved to Sussex, to University of Sussex, where he got a position as a professor of chemistry in the Department of Chemistry. So he he's an author of more than 100 peer-reviewed papers, so it's an impressive record track. But I wanted to mention also the awards he received, especially the Sir Edward Frankland Fellowship of the Royal Society for Chemistry, and then the Alexander von Humboldt Foundation Fellowship. So he received it, I think, twice. I've seen in the CV. And then let me tell you something about his research activity. He mostly studied, especially recently, molecular magnets. So he has many publications in the topic. And when I had the pleasure to meet him in 2019, probably in the last, it was the last in-person conference, international in-person conference that I've attended. And then he was 1 year after his breakthrough discovery in 2018 of the high temperature molecular magnets. So these are molecules based on dysprosium, and they have they can show magnetic stability up to 80 Kelvin. So in principle, one could think of using these molecules even with liquid nitrogen temperature. So today's talk will be partially about this topic and other things that he's gonna tell us. So Richard, stage is yours.
Okay, thank you very much, Fabio. I should start by, of course, thanking you for the invitation and for your efforts in arranging this talk today, along with your colleague Seo Kyung, who's been very good at helping set everything up this morning. I have to just preface my talk by saying something that I said to Fabio as well. About 4 or 5 days ago, I completely lost my voice, and it is gradually returning. This week I have 3 undergraduate lectures to give, so I'm having to sort of ration the volume with which I speak. So if my voice cuts out at any point, okay, that's not unexpected. There's nothing wrong with your computer. It is my voice, okay. So we'll soldier on. So as Fabio said, I've been in Sussex now for about 3.5 years. There is a tourism slide at the end if I have enough time, but just to give you a snapshot right now. So Sussex is a county in the south of England, located in the city of Brighton. So it makes it relatively unusual in the sense that the university is strongly connected to a city which is famous for its beaches and its coastline and all the fun things that come with it. Okay, so it is a really fantastic place to live and to work, and probably the best place in the country to be a student, I would imagine, as well. So if any of you just happen to be in the local area, we're about 1 hour to the south of London, very easy to get to. And if you are in the area, please do let me know. I'd be very happy to show you around. Okay, to the science. So I guess I'll begin with an overview slide. Click on there. In terms of the work that we do. So I am mindful of the fact that the majority of people in this seminar today are not chemists. Okay, so I will take that one into account. And I have one very, very brief tutorial slide, which I hope you will find useful. If you are a chemist, you can switch off and check your email for a minute or two. But in a few slides' time, I'll just give you a little bit of background in terms of the chemistry nomenclature, which I think it's important for you to know, because if we don't do that, then much of what I will say won't make a great deal of sense. Okay, but very broadly speaking, I'm a synthetic chemist with interests in molecular magnetism. I work with compounds known widely as organometallic. You may know them as metal organic. They're more or less the same thing with a few subtleties. But the main difference is that we're predominantly interested in interactions between metals and carbon, okay, which is a vast field of research for many different reasons. But in the context of molecular magnetism, before we really started focusing on this, people weren't particularly interested in the magnetic properties of these compounds. So I spotted what I thought was a gap in the market, if you like, and it turns out to have been a very fortunate choice, because it's led to quite a lot of interesting discoveries, especially in this field known as single molecule magnetism. So we're interested in so-called sandwich compounds, and cutting a long story short, a sandwich compound effectively, if I get the cursor going here, Here's an example of a sandwich compound in which you have a metal. This is the green ellipsoid in the middle there, sandwiched between two organic bits, if you like, as well. So this is the broad idea of a sandwich compound, which I'll expand on in a bit more moving forward. But in terms of the general structural motif, we're interested in putting a lanthanide between two 5-membered rings. And this is interesting from the perspective of single molecule magnetism. The sorts of compounds that fit this description are referred to as metallocenes. The 5-membered ring has been known in lanthanide chemistry for probably since the 1950s, I think. So, you know, the chemistry is well established, but the magnetism is not. More recently, we've switched from the 5-membered ring to a 4-membered ring, known as cyclobutadienyl. And here the chemistry is very new indeed. The first examples we published about 3 years ago, and we're gradually starting to look a little bit more into how changing from a 5-ring to a 4-ring impacts on the magnetism. I'll talk a little bit about some unpublished work in that area today. So most of the talk will focus on the lanthanides, or the rare earth elements. Okay, but we are interested more broadly in the F block as well. And alongside the lanthanides, you have the actinides. So these are the radioactive elements, most of which are man-made, but they're naturally occurring up to uranium. So since we moved to Sussex, we inherited about 2 kilograms of uranium. So we've been exploring some properties involving uranium sandwich compounds. You can see here with an 8-membered ring and a 4-membered ring, and also again the 5-membered ring. They're not so much interesting from the perspective of the magnetism, more the structure, the bonding, but especially the chemical reactivity. Okay, so that's the reason why I'm not really going to focus on this work today, but safe to say we're interested in unusual oxidation states and their reactivity. Okay, so today's talk will focus primarily on the lanthanide chemistry. Okay, back to the magnetism. Any of you who've been to a single molecule magnet talk at any point in the last 15 years will have seen a slide that looks something like this. It's the sort of thing that people working in the field like to do to create a sort of familiar reference point and then try and tie it into the chemistry that they want to do and then dial up some magnetic properties. So the analogy that kind of gets drawn between single molecule magnets and classical magnetic materials is that SMMs are some sort of molecular ferromagnets. Okay, there are some inconsistencies in that because ferromagnets pretty much by definition have exchange coupling across large domains, whereas molecules are essentially just dots. Okay, so there is an analogy there, but in terms of the properties, they kind of have the same property, which is magnetic hysteresis. In the case of a classical magnet, it arises from cooperative interactions across domains, whereas with a single molecule magnet, it arises genuinely from the properties of an individual molecule and not interactions between them. So people have taken this analogy, if you like, with a classical physical property and said, well, if you can use this as the basis of a computer hard disk drive in the case of a classical magnet, maybe you can do the same thing with a single molecule magnet. So it's a very simple premise. It may or may not be correct, but it's certainly used quite a lot to put things into context. In terms of motivation for exploring this idea, okay, we can attach this to a dollar figure. It's taken from a non-peer-reviewed source, by the way, so take it with a pinch of salt, but in a couple of years' time, the data storage market is going to be valued at a big number. So whether it's accurate or not, it's always going to be a very big number. So the way that things seem to work at the moment is that mankind is generating a lot more information at a much faster rate. So what we need are innovative ways of storing and processing that information. And this in principle is where molecules could come in. So the idea is that you can take the same property and reduce the scale on which you observe it. Okay, so here is an example of a different type of sandwich compound. A terbium atom in the middle between two phthalocyanine ligands. This one I've picked out, it's aging quite nicely now, nearly 20 years old, but this was the really, really important compound that, for me at least, sparked my interest in the field, and that applies to many other people too. So it's the work of Ishikawa. And what you found in these so-called phthalocyanine sandwich compounds, that you can indeed observe magnetic memory in a compound that consists of only a single spin-bearing center, which is very, very different to previous single molecule magnets, which were based on elaborate transition metal cluster compounds, and certainly very different to things that consist of, you know, something like Avogadro's number of unpaired electrons. So there's a very big difference there as well. So this basic design principle, a lot of people have picked it up and tried to run with it. And essentially today's talk it will be my take on how we've picked up this idea and tried to develop it. So the idea is we're trying to observe magnetic hysteresis at the level of single molecules in a way that introduces magnetic memory effects. In terms of the overall field now, it's evolved quite nicely over the years. And I think for me, coming at it from the perspective of a synthetic chemist, which I essentially am, It's genuinely multidisciplinary in its flavor. And this is good for so many reasons. And from the point of view of a chemist, it really forces you to try and learn some physics. And I would hope from the perspective of a physicist, it kind of tries to force you to learn some chemistry, hence why I'm talking to you now and why I've listened to other people from physics backgrounds discuss this in the past. So it's interesting and it's challenging, and we don't understand all of it. And that is kind of the motivation for carry on in this area. So the recognizable part for me is where it involves molecules. I'm just picking some highlight studies from recent years. A group, I think, in California have been able to use STM tips to demonstrate magnetic coupling between individual molecules. And you notice this example involves sandwich compounds, one on a surface, one on a tip, and you can detect things like exchange coupling interactions at the level of single molecules rather than in bulk. I guess the work that is coming out of QNS in South Korea is some of the most eye-catching of all, where, you know, even smaller than molecules, you can start to observe magnetic memory effects in single atoms on surfaces. And certainly you notice it in the chemistry literature as well. Work such as this is really starting to draw a lot of attention. I think reassuring from my perspective is that I may not have a strong grasp on the physics, but in a more overview, general sense, many of the general conclusions coming out of work like this seem to be broadly consistent with what the chemists are saying as well. So that's quite reassuring moving forward, that the physical picture may be different in an exact context, but in a general sense, there are clear similarities. And then back to a sandwich compound again over here as well. This is from the work of Jeff Long's group in Berkeley. This is a magnetic hysteresis curve for a molecule consisting of 2 terbium ions. And you can see in terms of the hysteresis loops, okay, they're pretty wide. The coercive fields are really enormous. And this is originating from within a molecule, not from something like a neodymium magnet or a samarium cobalt magnet. So the magnetic properties can be pretty ferocious in these things. But in terms of moving the field forward, I guess one of the challenges that has emerged is relating to, especially to temperature. Okay, so obviously fields such as this will have supporters and they will have critics. Okay, and the critics are perfectly valid in saying that fair enough, you can do these things, but isn't it a little bit cold in terms of making a functional device? That may well be true. Okay, but from a fundamental perspective, there's nothing wrong with that. Okay, maybe you can adapt the setting to fit the property that you observe at a specific temperature. But a different way of approaching it, of course, is one of the challenges: can you take these properties and can you start to observe them at higher temperatures? Okay, so that is one of the challenges that we and other people are working on. There are others, which I'm not going to talk about too much today. For now, we'll just focus on the temperature aspect of it. So cutting a long story short, when it comes to single molecule magnets, I think it probably is true to say that the lanthanides, or the rare earth elements, they do dominate the field quite a lot, and they've kind of taken over from transition metals, which were influential right at the start of single molecule magnets in the 1990s, especially manganese. But it was eventually realized that it's not so much the number of unpaired electrons that really matters, but it's the spin-orbit coupling. Okay, so you can have a system with as many unpaired electrons as you can conceive of, but if you don't have any magnetic anisotropy or spin-orbit coupling, no SMM. Conversely, if you have only one unpaired electron and you have a lot of anisotropy, you may well observe single molecule magnet behavior. Okay, so the key property really is spin-orbit coupling leading to magnetic anisotropy. So it's perhaps not surprising then that people eventually switch to the lanthanides. There are multiple reasons for this. If you want a very simple reason as to why lanthanides, and not all of them, by the way, it tends to be the group of 3 or 4 just to the right of the gadolinium on the right-hand side of the F block. Dysprosium is by far the most popular, and the short explanation is that it's magic. Okay, that's not my words, but the words of Dante Gatteschi, who was the original pioneer of this field as well. But I think he's being a little bit modest there as well. There was a lot of thought that went into his work in this area. So dysprosium in its common tri-cation state here has a 4F9 configuration. This gives a ground term, which you can see has really significant LS coupling in the context of the Russell-Saunders scheme. It gives you a J value of 15/2 in the ground state. So there's an awful lot of inherent magnetic anisotropy in species such as this. So dysprosium is a good one. Terbium also works. Holmium works a bit as well. And after those 3, the number of other lanthanides involved in this field is generally pretty small, mainly because the spin-orbit coupling is not quite as strong. So in terms of the dysprosium, if you like, this is the ingredient that nature gives us to work with. And what we're really aspiring to do as chemists is to control these physical properties. So how do we control that? What is the handle? Well, we're interested in how the metal ion interacts with its environment. So we're interested in the crystal field. we're interested in the chemical bonding, for example. So with lanthanides, it's generally accepted that the bonding is predominantly electrostatic, but there is a small covalent contribution. And the question is, does that matter? I'll explore that later in the talk. We're also interested in how the chemical environment is arranged around this metal end. So we're interested in the symmetry of the coordination environment. That really does matter in different ways for different lanthanides. And if we're talking about systems where, excuse me, we're talking about interactions between paramagnetic centers, then we're obviously interested in the exchange coupling. So that's the natural ingredient, and this is what we're trying to do, to try and influence the properties of interest. So how do we do that? What's our design principle? Well, looking at it at a qualitative level, what you see there is a picture or a cartoon of a molecule that would give you the ideal scenario for an SMM based on dysprosium. So it's fairly well established that this 4f9 electron density of dysprosium can be represented in a simple sense by this sort of what they call an oblate picture. Okay, so squashed along the z-axis and stretching into the xy plane. And the idea is you want to use the chemical environment to enhance this magnetic anisotropy, which you will achieve if you put your ligands trans to each other and above and below the dysprosium and shown like this, which would give you a so-called perfectly axial crystal field. And what you also want are no interactions in this XY plane here, otherwise known as an absence of an equatorial crystal field. Okay, it's probably true to say that a molecule or an ion of this type has not been isolated and stabilized chemically. Okay, so it kind of is the aspiration. In terms of how close you get, however, that's kind of what we're interested in, and we'll try and build up a picture of where we get close to that, but not quite perfect. So in terms of the molecular structure, this is fine. How does it relate to the electronic structure? Well, in terms of the crystal field splitting, if you take this term and put it in an environment like this, okay, you have 16 crystal field states, which turn up as Kramer's doublets. And in this particular environment shown here, your ground Kramer's doublet will adopt the maximum value of MJ because of the axial crystal field. And again, if you fix the geometry to being ideal, the Kramer's doublets kind of stack up, if you like, in numerical order like this. So I'm only showing 4 pairs of them here. There are some others going up over the top, just to condense the diagram, they're not shown. So the chemist's way of interpreting a diagram like this is that if you can populate one of these states instead of the other one, your molecule will have a preferred magnetization direction arising from the anisotropy. And if that situation persisted at all temperatures, you would have a permanent magnet, okay? Problem is, of course, it doesn't persist at all temperatures, and relaxation from one component of the ground doublet to the other is not only facile, it's also possible to occur via multiple mechanisms, okay, which I've illustrated here with these numbers. So if we go for thermal relaxation, it's generally accepted now that the thermal relaxation is initiated by the system absorbing phonons from the lattice. And what you can do essentially is undertake a series of quantized transitions, which you may or get over the top and go down the other side. But normally what happens is rather than going right over the top of the barrier, you tend to cut through it at some point. Okay, and this is fairly well defined in terms of Orbach processes, which as physicists you probably know lots about. So that's step one. And as a chemist, what we're trying to do is maximize relaxation via this route, via the highest possible barrier. Okay, and that gives rise to something called U-effective anisotropy barrier. The problem is that nature is much smarter than that. Okay, nature can relax via other mechanisms that are considerably harder to control. So for example, you can go even straight through the barrier in the ground state in a step that's known as quantum tunneling. Temperature independent and is extremely common in pretty much every single molecule magnet known. Okay, so switching this off is really challenging. There are things such as Raman processes as well, which occur via virtual excited states, and controlling the Raman processes, as far as I can tell, is practically impossible. If they happen, they happen. If they don't, then you got lucky, I think. So as a chemist, what we're trying to do is influence what is already looking quite a complex picture. So this idea of control may be a bit aspirational, okay, but at least if we try and control the chemistry, we can try and influence things in a well-defined way. And essentially what I'm going to do today is tell you a bit about our success, or if you like, lack of it, in controlling this picture.
Richard,
yeah.
Before you move on, let me ask you a question here. So,
please.
Of course, you pointed out that our STM atoms on the surface, or any rare earth on the surface, is somewhat similar if you put it on a polar material such as MgO, right? We're sitting on the oxygen side, which is negatively charged, but we're lacking the second negative ligand on the opposite side. So. Yep. I would, to first approximation, assume that doesn't really change anything. But what do you make of that if you had an asymmetric situation like that?
So I think you are right in saying that, definitely, because the crystal field remains axial. The question is maybe in terms of your surface molecules, if you have other oxygen atoms interacting in some way. So the only study of an isolated rare earth oxygen diatomic species, maybe you know this, is the Chibutara theoretical study, where he has one dysprosium and one oxygen. And if I recall correctly, even for that system, which by definition has to be perfectly axial because it's in the gas phase, the G tensors for that, they don't even reach the axial limit. GZ does not hit 20. So even in a sort of hypothetical species, which by definition is purely axial, you don't fully get there. So I think in your case, that's about as close as we can get, actually. But what I don't recall from your work is if the other oxygens present on the surface have some interaction with the rare earth as well. Is that the case or not?
Well, you know, obviously, if you take something like MgO, you have then the next nearest neighbors would be positively charged magnesium in the C4 symmetry, right? And then you have more oxygens further away. But we don't usually think about those very much, but we have to consider the fourfold symmetry due to the magnesiums.
Yeah. So perhaps I should emphasize, at least with this system, this is referring to an isolated molecule in a gas phase, right? So I think, I mean, in terms of design principles, your systems are about as close as we get. I think everything else has much more significant axial contributions. Is that okay? Shall I carry on?
No, thank you very much. Perfect.
Okay, thanks. So that's the general design principle. So next is a bit of a leap from the basic design principle to some real molecules. Okay, so try and keep this picture in mind as we move to the next slide. And I draw your attention to these molecules shown over here and this one. Okay, so this is the point at which the chemistry content, I guess, becomes a little bit more unfamiliar. So what I'm going to do from this point is, in a second, switch to the tutorial slide. But what we're trying to do at this point, in terms of a cartoon representation, is our metal. Here's our axial crystal field, and it is generally difficult to isolate a purely axial system because very often, you know, lanthanides have quite large radii. Other ligands or other chemical entities in the system will interact as well from different orientations. So really, the picture I'm going to build up is taking this basic design principle and modifying it in a way that does it by these X atoms. However, before I do that, I think I need to explain to you in a little bit more detail what all this really means in terms of chemistry. Okay, so here is the tutorial in organometallic chemistry for physicists. Okay, so if you do know this, please accept my apologies for pitching it at too low a level, but I think everybody else with physics backgrounds may benefit from this a little bit. So my assumption is that everybody's heard of benzene. Okay, so benzene we normally represent like this, but we don't show the carbon atoms. There are hydrogen atoms implicit on the molecule, but we usually just get rid of them for convenience. Okay, so this is how a chemist draws benzene. Notice that the double bonds, single bonds alternate around the ring like this in the two systems. So overall, we show this delocalization in the form of a circle. 6 pi electrons, Huckel aromatic, no formal charge on the molecule. Okay, that's the case with the 6-membered ring. With the 5-membered ring, it's similar in many respects, but different. Okay, so I mentioned at the start this 5-membered ring. It starts off with 5 carbon atoms and 6 hydrogen atoms, but to create the analogy with benzene, you have to get rid of one of the hydrogens, which you remove as a proton, which leaves behind the negative charge. The negative charge you can then push into the ring, move the negative charge out, then negative charge back in, negative charge out like that. Effectively, what happens is this negative charge works its way around the ring so that it spends 20% of its time on each of the carbon atoms, so that overall we represent it like this. It is basically the same as benzene. It has 6 pi electrons, it's aromatic, but the really big difference is it has a charge of -1, which tends to mean that its interaction with metals is stronger, okay? So if you take 2 of these CP groups and you put them either side of a metal, you end up with a sandwich structure. Okay, I'm not showing the synthetic chemistry, this is just the outcome. Here is a sandwich. And the nomenclature that I use as well, you'll often see this referred to as eta5, which is a term called the hapticity. Okay, any classical Greek scholars in the audience will know where that word comes from, but it basically refers to the number of atoms that the 5-membered ring interacts with the metal at the same time. Okay, so 5 atoms interacting from the ring gives eta5. This structure is known for every metal in the periodic table, pretty much. With a transition metal, the bonding is usually covalent with some ionic, but with a lanthanide, the bonding is predominantly ionic, but with a small amount of covalence in. This is the bit that actually matters. because the covalency occurs from the metal interacting with the lanthanide 5d orbitals, and this is where the crystal field comes from. Okay, so in the case of dysprosium, it will be an axial crystal field, and this is what the electrons in the 4f orbitals will experience. Okay, so that's the basic design principle. So if that wasn't too complex, we'll go back to the molecules, and I think on that basis you can see now where the design principle comes from. So this is a ChemDraw cartoon. Okay, here is a real molecule with the structure determined by X-ray crystallography, which you can tell because these things are ellipsoids, thermal displacements, if you like. And what we can do with the molecular structure is undertake ab initio calculations, which allow us to interpret the electronic structure in a quantitative sense. And one of the things that's not necessarily obvious from the shape of the molecule is the orientation of the magnetic axes in the various Kramer's doublets. Okay, you can guess based on the symmetry of the molecule if you want to, but that's a little bit risky because there are many cases where the expected direction is actually not observed experimentally. So ab initio calculations are now regarded as normal for this field. We do this via collaboration. And here is an example of a dysprosium between two 5-membered rings with some substituents hanging off the ring. That's easy to do chemically. Dysprosium here, 2 sulfur atoms. What we find in this molecule is that the easy axis of magnetization, the ground Kramer's doublet, is pointing towards these 2 5-membered rings and kind of perpendicular to this 4-membered ring here as well. That's the case with sulfur. The picture does not change at all if you change sulfur to any of these atoms listed here. So we can start to develop what we refer to as a magnetostructural correlation or a structure property relationship. And this is one in which our easy axis of magnetization will be defined as orientating towards the 2 5-membered rings. This is the electron density of dysprosium illustrated in cartoon format. And these are the equatorial ligands. If you like, they're going to fight the axial crystal field by providing a similar interaction in the equatorial direction. So this is a chemist's view, I think, of magnetic anisotropy. It's a little simplified, but simple is good at least to start with, okay? So chemists kind of, they discovered, in inverted commas, this in 2011, but it turns out the physics community knew about this decades ago, okay? So the chemists have been busily rediscovering things that the physicists have known for a very long time, which is quite funny. So in terms of the general picture, this is our basic model. The evidence to support that the model work is ultimately we're going to say that this basic framework is well suited to SMM behavior. Here is the evidence. Okay, so this is kind of a rogues gallery of molecules that we've made over the years. We've made many more since then as well, but there's no point putting every single one of them on, but they all contain the same basic unit, which is a 5-membered ring with a metal sandwiched in between, and they all have some other ligands in this equatorial plane. Okay, so all these compounds are SMMs to varying degrees. Eventually, of course, you have to start to make sense of this in a slightly more quantitative fashion. And I think the 3 compounds where we started to spot a periodic trend, okay, which as an inorganic chemist is something you're always on the lookout for, were the ones in which the dysprosium sandwich was bridged by a phosphorus atom, an arsenic atom, and an antimony atom. So the reason why, of course, this is a periodic trend is that group 15 of the periodic table runs nitrogen, phosphorus, arsenic, antimony, bismuth as well. And what we saw as we moved through this series was a gradual increase in this so-called effective energy barrier. Okay, so if we take the 3 specific compounds and interpret them in terms of this model here as well, what we find in terms of bond lengths and angles, there's no real change in the sandwich unit, but the distance to these X ligands gets bigger as you move through the series because the atoms are getting bigger as you go down the group. What this is essentially telling us is that the SMM properties arise from this sandwich unit here, but the ligands in the X positions, I've been showing them, they attenuate the properties. So if you move them further and further away, the properties should increase, provided this thing doesn't experience any significant distortions. So we went one further to another X ligand. It doesn't really matter what the bits of it are. It's a diamagnetic bridge between the 2 dysprosium. But in this system, the oxygen atom bound to dysprosium is much further away and interacts much more weakly in dysprosium than it does with any other case. And sure enough, the barrier jumps up again. So this model that we're starting to refine now is looking as though it has some sort of at least predictive capacity, which is what every good model should do. That, of course, is the case with the energy barrier. What about the hysteresis? Well, not looking so good here. The presence of these equatorial X ligands basically kills the hysteresis. It limits the temperature at which you observe it, and it also gives you these so-called waste restricted loops, which means no coercivity, no remnant magnetization of any significance. So when we analyze,
are you gonna talk a little bit about what the measurements are?
Yeah, that's coming up. Actually. Yeah, that'll be maybe in the next slide actually. So this is a standard hysteresis curve, and what we found when we analyze these things computationally is that you see a lot of mixing between the various wave functions, which facilitates the interaction. It's facilitated by this equatorial interaction. So then the hypothesis we refine is effectively if you get rid of these things completely, maybe you reduce the extent of mixing between the various states and the properties will improve. So ultimately then it became apparent that these X ligands in this plane are getting in the way. So the question was, can we make a system in which they're gone completely? Can we make something that looks a little bit like this? Okay, so we have a 5 ring with some, if you like, bigger organic stuff on the edges here. It doesn't matter what it is for now, it's just bigger than it was previously. And what we can do is make a precursor compound that looks a little bit like this. And what you're aiming to do is to get rid of this boron hydride group over here. Okay, I won't go into the details of the chemistry, but it requires a fairly exotic reagent which kind of rips this to pieces and it disappears as volatile compounds. And sure enough, you can make this cation in the presence of an anion which interacts very weakly, and certainly not directly with the dysprosium because the charge density is extremely low. Okay. So we have been able to synthesize a system in which we have none of these X ligands. There's no real interaction between the substituents. Okay, we're not perfectly at linearity, so the angle along these dashed lines here between dysprosium is 162 degrees, and the distance between dysprosium and the center of these rings is relatively short. Okay, so the aim is to make the geometry as linear as possible, to make it axial, and to have these dysprosium carbon centroid distances here as short as possible so that we have a strong axial crystal field. Okay, so the emphasis is the crystal field must be strong and it must be axial, not one or the other. Okay. So here are some measurements. So these are AC magnetic susceptibility data shown on the left. And what you have is a plot of the in-phase and the out-of-phase susceptibility. That's what chemists call it. I guess the physics community refer to it as the real and the imaginary components. And what we're seeing in the imaginary component down here as well is well-defined maxima at a specific temperature and frequency in this range. So this is a standard NPMS measurement, I think. And the maxima persist up to about 130 Kelvin, which on its own may not mean a great deal actually, but when you compare it to what's out there in the literature, this is way higher than anything that had been measured before. Okay. So from these maxima, you can start to extract characteristic relaxation times for each given temperature using established methodologies. So what you can then do is plot the relaxation time as a function of reciprocal temperature, and it gives you a plot that looks a little bit like this. So we have a high temperature region in which the dependence is essentially linear to a point. We have a low temperature region in which the relaxation time is essentially temperature independent, and we have this kind of crossover region in between, which is indicating that you have mixtures of different relaxation processes. So the analysis that we apply to this is the same that everybody else applies. In the high temperature, you have dominant Auerbach relaxation. At low temperature, you have quantum tunneling processes, and in the middle, you probably have all three, and you have these sort of Raman processes taking place as well. So the headline figure that comes out of this is the energy barrier, which is about 1,540 wave numbers. What I forgot to do was to convert this to Kelvin, because my physics colleagues tell me that you don't always like wave numbers in the physics world. So I think it's about 2,200 Kelvin as a rough calculation, which is way higher than anything that had been measured before, either by us or by anybody else. So that was pretty good. Quantum tunneling time is very slow, which is what you want as well. This is also significant because potentially it gives you an indication as to what the hysteresis might look like. In principle, it should be pretty good, actually. So in terms of the hysteresis, again, we have a bit of a mismatch between chemistry and physics. Chemists like to talk about hysteresis in terms of magnetization, in terms of Ørsted, and not B in terms of Tesla, but there's a factor of 10,000 difference, so that's easy to work out. And what you see from the low temperature to the high temperature regime, first of all, low temperature, these loops are wide open, okay, and very little drop indeed when you get to zero field, and coercive fields in the region of about 5 Tesla, which for a single molecule magnet is very good. Increase the temperature, the loops start to collapse, of course, and about 85 Kelvin they remain open, but the key qualifier here, of course, is that the scan rate is actually pretty fast, okay? So the easiest way to increase your blocking temperature in an SMM is just to scan the hysteresis faster. That's kind of cheating. Okay, so It's important also to do it at a scan rate dependence. And when you get it down to a level that's about as slow as you can manage with a standard machine, what you find at 80 Kelvin, that is, these loops are still open, okay? So the significance of this was that it was the first SMM that stayed open with the hysteresis loops above liquid nitrogen temperatures, which is why this thing seems to have attracted the label of being first high temperature SMM, which I guess is the analogy with superconductors. Okay, maybe distorting the significance of molecular magnets, but that's the analogy, if you like. So this is good for a number of reasons. One, the properties are what they are, but also it seems to be consistent with this very basic design principle that we proposed based on some preliminary results. It does seem to work. But inevitably, it's a little bit more complicated than that. And obviously, we need to look at these things at a microscopic level using quantum chemical calculations. And this is where we've been able to initiate a very successful, with an early career researcher in Finland, Akseli Mansikimaki. So this is where I fly the flag for an early career researcher. Akseli is not so long out of his PhD, but his level of understanding and his clarity of explanation is absolutely remarkable for somebody at such an early stage of his career. Okay, so anybody interested in ab initio type calculations on molecular magnets, my suggestion would be contact Akseli, because he's really fantastic. So this is the crystal field splitting for this cation shown here. This is the experimental structure, by the way, not optimized. So these are the X, Y, Z coordinates from crystallography. And what you find, based on, is that the splitting structure is about as close to perfect as you can get in a real experimental system, because it looks like the predicted theoretical version for a perfectly axial system. And what you will find is that each of these individual Kramer's doublets is described by a well-defined wave function up to about sort of this level. Then the mixing becomes appreciable. The dominant relaxation pathway is shown by these blue arrows, okay? The red arrows represent other pathways, and the darker the shading, the more probable it will be, but it's basically telling you that this system should relax by the first, second, third, fourth excited Kramer's doublet, which corresponds to a barrier just above 50 and 100 wave numbers, and conveniently, that's what we observe experimentally. Okay, so this is really good. The question is, of course, where does the energy for these quantized transitions come from? And of course, this is where we start to look at our simple model and say, perhaps we're being a little bit too simple here as well. So I guess one of the active theoretical discussions and debates in this field right now is where these transitions originate from. And it's generally thought to be the case that spin-phonon coupling, so these sort of periodic lattice vibrations, find a way of coupling with the electronic system, structure of your molecule. Okay, so the gap from here to here is about 670 wave numbers. And what we've found is, or rather what Akseli has found and explained to me, is that we have a molecular vibration which looks like this. Now, I realize over Zoom that animations don't always come across quite smoothly, but what you should be seeing here is one of these 5-membered ring undergoing a sort of flexing or a deformation. Okay, so this is a molecular vibration which is stimulated by absorption of a phonon, and that gets you from here to around here. And what Akseli was able to do was calculate every molecular vibration for the entire cation, which is extremely time consuming. And again, on this slide, what you should be seeing is 6 forms of molecular motion of different types. Okay, so you can see the 5-membered ring in these two kind of, it remains as a 5-membered ring and is flat, but is tilting across here as well. Then the ones along the bottom, you can see the ring deforming as well. So these are thought to be the key molecular vibrations that are forcing this system to relax across the structure that I showed on the previous page. So this has implications.
Quick question. Yeah. When you make a crystal, I assume you put in some diamagnetic molecules, right, to not have one molecular magnet next to the other one, or can you just make a pure compound like this and not have too much interaction from one to the next?
That is a very good question, actually. So the standard way of doing this, of course, is to make the yttrium version of this compound, which of course it has no unpaired electrons. The problem is that we couldn't synthesize that compound, which is very unusual. Normally dysprosium and yttrium have the same chemistry, but to this one we couldn't do it. So the short answer to your question is no, that we didn't do that. What we rely on, however, is that this cation here, of course, comes with the anion, and the anions sit in between the spin-bearing centers. So we rely on that helping. The distance between dysprosium ions, I think, is about 12 angstroms. So we assume that a distance of 12 angstroms is long enough for the exchange coupling to be negligible. Okay, so we can't definitively answer the question, okay, but we don't think that is a significant issue with this system. So back to the simple model, it clearly needs a degree of refinement, because I've said strong axial crystal field, that's all you need and everything will be fine. But clearly there's more to it than that, because if we want to push this property further and further, we now have to start to control the molecular vibrations that are busily rocking away on your screen right now. This is very difficult, and I may even go so far as to say it's practically impossible to do. So we need to find an alternative approach. We have some ideas as how to do that, which are kind of underway in the lab right now. One of them I'll talk about right now will be the effect of including, if you like, heavier oscillators in these 5-membered ring. And what we've been working on at the moment is what happens when you include phosphorus. Okay, so phosphorus, in terms of the periodic table, has a diagonal relationship with carbon. And it's often referred to as a carbon copy. So we thought if we put a heavier atom in here, maybe this will have some effect on the molecular vibrations. And that was the basis of the hypothesis. Okay, so not very strong, more exploratory. So we can make this cation shown over here. I won't talk about the details of the chemistry, but basically you make a compound that is essentially isostructural to the cation I talked about previously. It's a little bit more linear, and the bond distances are about the same. So structurally, it's about as close as you can get. So we were pleased with this, and then we went away to measure the properties, and the AC susceptibility comes back looking like this, which confused us, I think it's probably fair to say. So normally what you have at a given frequency or a given temperature is a single relaxation process. And what we've found for this system is that we actually have two, separated by some way, actually. We've checked the phase purity. We're pretty convinced that we have a single phase at 100 Kelvin. We've done X-ray crystallography at 30 Kelvin as well. There's no change in terms of the overall properties. And if I show you all of the data and then zoom in a little bit, we're clearly getting two bunches of peaks. We have a high temperature regime, which kind of gives way to a low temperature regime as well. So this confused us for a while, but it effectively is starting to challenge this really simple model whereby you regard relaxation of magnetization as flipping a magnetic dipole from up to down, okay? Because here it seems to be happening twice. It doesn't really make a lot of sense. In terms of the properties though, however, if I come back to the AC data, we can determine two barriers for this thing, one of which is about twice the other one, but not exactly, which we think this is a coincidence, but we're aware that it might not be. And in terms of the hysteresis as well, it's pretty good, but we're seeing additional effects over here as well, these sort of little drops, which we're not confident in the explanation of these per se, but what we have been able to do is calculate the presence of two different spin phonon coupling regimes, whereby one of them becomes more preferential to the other at lower temperatures. Okay, so we're still kind of working out why this system behaves in the way that it does, but if it highlights anything, it highlights that your basic design principles are fine on a piece of paper drawn by hand, but in reality, nature may well take a different course. Okay, so this is kind of a work in progress, I guess, that we're making some understanding of, but still scratching our heads about a little bit. In terms of the broader significance, however, the hysteresis is still open up to 72 Kelvin, so not quite liquid nitrogen temperatures, but up there with the best in the field. So in the last closing bit of the talk, actually, just looking at the time, I thought I'd just tell you a little bit about some more, if you like, chemical modifications that we're trying to make to this basic design principle. So here is the picture I've talked about a lot up to now. What we thought we would try and do to strengthen the nature of the axial interaction was replace the 5-membered ring by a 4-membered ring. Okay, so this is cyclobutadienyl. And this is different because it has a charge of 2- instead of -1, and it's more charge dense because there are fewer atoms. Okay, so the idea is to take something on these lines and make a compound that would look like this. And if we can make any of these, this should have some quite interesting properties. And again, that was the basic idea. Synthetic chemistry, it turns out, was extremely difficult. Okay, we discovered very quickly why there were no examples of systems like this interacting with a rare earth in the context of, well, any context really, not just molecular magnetism. So we initially tried to make a compound that would look a little bit like this. Doesn't work. Okay, I'm just going to talk a little bit about the chemistry, but I'll skip a few of these slides because the chemistry does get quite detailed. But if you just focus on the cartoon here, what we find is that these silicon substituents here, they undergo some form of chemical activation where the substituent, which previously wouldn't interact with the metal, now does. Okay, and you can see even from this simple picture, the direction it's coming from is going to compromise the axiality. We know why this happens. we think we are forming this compound, but as it forms, it actually reacts with the starting material to give this weird looking system over here as well. Okay, so that was the problem. We started with the potassium salt here. Okay, I'm going to skip past the SMM properties a little bit, and just to say that they're pretty boring. The hysteresis is pretty boring as well. But it does fit in with the broader picture that this equatorial interaction here, it kills the anisotropy. We then switched to sodium as the starting material to see if we could get something better. That's actually even worse, because now we lose the axiality here and we start to mess up the other ligand as well. SMM properties are similar to the previous example, not fantastic. Small barriers, no hysteresis. So eventually what we did was to try and make one of these so-called half sandwich compounds, in which we've changed the lanthanide starting material to get rid of the halide. And we've done the reaction as before, but only using one equivalent of the four-membered ring. So you get this basic sandwich unit, but it forms a sort of coordination polymer. But with this approach here, what we have been able to do is transfer this four-membered ring to the lanthanide without activating the substituents. Okay, so at least we've managed to transfer it intact to the lanthanide, which is reassuring. These are the crystal structures. You can see the four-membered ring here with the silicon substituents, okay, and they're far enough away from the dysprosium to convince us that this weird bond activation process we saw previously actually is not a problem here, okay. What about the magnetism? The two different compounds, one of them has got a potassium bridge to the four-membered ring, the other one has a sodium bridge to the four-membered ring. The AC susceptibility, okay, is not fantastic in the sense that the barriers are quite small, but they are reassuringly similar. The profile is thermal relaxation, high temperatures, quantum tunneling, low temperatures, quite a bit of curvature here as well, which is suggesting that Raman processes are more dominant in these systems. But the really important thing is not to consider these things, if you like, on their own merits, but a comparison to the five-membered ring system that I've talked about previously. So what we're looking for with the four-membered ring is an improvement relative to the five-membered ring. So do we see that? Really, where we're going with this, okay, so if we can start with this compound, which we know we can make and isolate, can we then replace one of these with a five-membered ring? So we have a four and a five ring, and then ultimately drive this to make a four and a five ring system, which you will see is structurally analogous to the compounds I talked about earlier on. Okay, so we've been able to make this compound with a four ring and a five ring, still with the borohydride shown here. So we now have a proper sandwich, and we have a barrier of 127 wave numbers. And again, that number on its own is not the important number. It will be the comparison of this compound with the cation that has, or the compound that has two five-membered rings. So let's make that comparison. At the bottom here on this slide, these are the compounds I've talked about previously. So we start with the five ring, so-called half sandwich. We make sandwich with two five rings and a borohydride, and then we make the sandwich with two five rings and nothing else. The barrier starts high, it goes down, and then it goes up a very significant amount. If we compare the four ring to the five ring, you can see that there is an increase of, let's say, about 50% in the barrier. So that's good. Then if we compare the two sandwiches with the borohydride group here, there's a very big increase shown in the barrier here. Okay, and then we compare this one with this one. Okay, so the kind of disappointing news is that we have not yet managed to isolate this compound cleanly. Okay, we think we've made it, but we can't get it pure. So we think we have made this compound, and if we can get it pure, what we're seeing here is a trend, admittedly 2 data points, okay, so not exactly a very clear trend. There is a gradual improvement in the properties. So if we can make this compound and isolate it cleanly, we think we will have a system in which the barrier shown down here actually starts to look pretty mediocre, and the hysteresis properties will look pretty ordinary as well. Okay, so we're close to getting this, but not quite there. And this is very much ongoing work in the lab, which I'm hoping to be able to report on in due course. So in a sense, that's kind of where we are. Looking at the time, that was a good point to stop, I think, as well. Hopefully what I've shown you is that synthetic chemistry does have a lot to offer, okay? And in terms of tying together molecular structure with magnetic properties, there are some appealing simplistic relationships that can take you a long way. But when you drill down into the detail of these things at a microscopic level, there are obviously complexities involved as well. But the lessons that we're trying to learn as chemists, you know, can we take these complexities and build it back into the chemical design? And this is the reason why we're moving in this particular direction. Okay, so on that point, my voice is just about holding out. I think it's probably an appropriate point to stop. And that always the people who've actually done the work. Okay, so this is the research group. The people in green are the ones who've done the lion's share of the work. Fusheng Guo was a postdoc in the group. He came to me as a Marie Curie fellow and stayed on as a postdoc. Dr. Guo is now Professor Guo back at the university in China. There he is, okay, at a group Christmas dinner pre-lockdown. And the rest of my group I'm grateful to as well. We have some very valuable collaborators, particularly like to flag Axial in Finland in terms of the funding. UK government sources and the Royal Society, and particularly grateful to the European Research Council for giving me a consolidated grant, which tragically now has ended, but never mind. But it was certainly a great way of exploring some unusual ideas that we've been able to bring to fruition. I mentioned at the start that I do a tourism slide. Okay, so here it is. Okay, Brexit has changed the nature of the United Kingdom. Okay, so geographically, we're very close to the UK, and in Brighton down here on the south coast, we're closer to most of France than we are to Scotland. Okay, so Brexit has happened, but if you do make it over to the UK, this is our relationship to London. We're an hour away by train. If you fly into Gatwick Airport, it's only 30 minutes. It's a very good connection to Gatwick. In terms of how Brexit is received, opinions vary, of course, as well, but there are a series of commemorative stamps as to how it may be represented in terms of overall national profile. If you do make it to Sussex, however, this is what is waiting for you. As you may have noticed, I give this talk a lot in China. Okay, so these slides are in Chinese, not Korean, so sorry about that, everybody, but you get the idea. This is the university campus. We're pretty unusual in the sense that the campus is located in the middle of a national park. Okay, so for miles around, you have open countryside, stunning countryside. Okay, this is the university campus. Chemistry is here. I guess the most famous discovery in chemistry was Buckminster fullerene, discovered by Harry Kroto in a lab that is 2 floors below me. And what I have in my office, I can show this a little bit later on, is I actually have Harry Kroto's original C60 samples in a beaker on my desk right now. Okay, so they're going to be going to a museum quite soon, but as a piece of history. This building here is Brighton and Hove Albion Football Club, who play in the Premier League. Okay, so if you come to Sussex, you can see that as well. This is what the city looks like under normal conditions. Pre-pandemic, we have lots of architecture, very diverse city as well, a great place to visit. And if you're in the area, like I said, please do let me know. Okay, so just to finish then, I'll thank you for your time. Thank Fabio and Seo Kyung again for the invitation today. And if you have any questions, I'll be very happy to take them. Thank you.
Thank you very much, Richard, for the amazing talk. So as usual, we open our meeting for questions. Mostly welcome our student questions. So please, if you have any question, just go ahead and mute yourself. Just give Richard some break if he has to recover his voice, maybe.
I'm still going, don't worry.
So maybe just because I'm too curious to wait, I have a question myself actually about this AC susceptibility of these molecules that shows 2 peaks in the imaginary component.
Yeah, there we go.
Yeah, so that's quite interesting. So how can we understand the mechanism? Because normally when you have like this peak of the imaginary component of the AC susceptibility, normally we picture out like low frequency. It means that our spin can easily follow the oscillating field that we apply. Then in resonance, there is some interplay between the frequency of the field that we apply and the dynamic of the spin. And the high frequency, normally we say the field is too fast for the spin to follow. Yeah. But here it looks like it happens for the first peak, but then on the second stage, there is an even higher frequency. The spin has another way to catch up with the frequency of the applied field. So what is actually what's going on? Do you have an idea about that?
We have an idea, but we don't know if it's right or not. So the first thing you immediately assume when you see a system of this nature, that there is an impurity present somewhere in the molecule. Okay, so we went to great lengths to exclude the presence of an impurity. So we know when we do the chemistry, there is a byproduct, but the byproduct is present in such small amounts it cannot possibly contribute to the relaxation in such a way Okay, so we've done powder diffraction, and the system is definitely phase pure. We've done variable temperature single crystal X-ray diffraction. There is some disorder present in the molecule, but what Axial was able to do with that was that the two disordered components, you can kind of calculate them separately, and their doublet structure is basically the same. Actually, the disorder doesn't have a big impact on that. So we have ample evidence to suggest, first of all, that there isn't an impurity present in this particular system. In terms of just a prima facie explanation of these two properties, it's very hard to say what it is. And again, we became reliant on the calculations here. So what Axial was able to do was to determine that a second relaxation process should occur with a finite probability. The only discrepancy with our work was that the calculated barrier for that process was significantly less than the one that we observed experimentally. So there's a bit of a disconnection there as well. But what he was able to do with the analysis in more detail was propose two different spin phonon coupling regimes, which one becomes dominant at high temperatures and then at low temperatures gives way to the other one. The explanation we have beyond that doesn't really go into much more detail. So we decided that we were thinking about this way too much, and we almost ready to put it out to peer review. It's pretty much ready to go, I think. So the spin phonon coupling regimes we think are temperature dependent. Whether or not it's related to the phosphorus, we don't really know. Okay, so it's kind of an open question at the moment. So it's not a very satisfactory answer to your question, but the spin phonon coupling regimes seem to be different at different temperatures.
I see. No, I mean, I understand that this is quite an open option of the research. So that's
I should say as well, actually. So there is a related compound that had been published by another group where they predict two processes, but they don't observe them experimentally. Whereas we do observe them both. So it's not just those along these lines, I think. I mean, to get SMMs with two different relaxation processes, actually, it's not so unusual, but they usually occur through things like, the presence of disorder or polymorphs or phase changes, things like that. But this doesn't seem to happen in this case.
Yeah, because if you have two relaxation processes, in the end, I guess the one that occurs at lower frequency will at some point dominate. I guess so. You need to have specific configuration to see this happening twice, right? It's not just if you have multiple relaxation, you see this.
But the other weird thing about this graph, I mean, I'm interested to know what your opinion is. You know, with the low temperature process, as soon as that one stops, the other one starts. There's no real overlap, which suggests that they are independent of each other.
Right. Well, thanks a lot. So anyone in the audience with more questions?
Yes, I want to ask the question.
Sure.
Please.
Yeah, I have two questions. So the first one is, I don't know how much effect of the angle between the ring and the lanthanide atom effect to the anisotropy barrier.
That's a very good question, actually. So it affects it a lot, but only up to a point. So not with these particular systems, but with some broadly similar, if you like, two coordinate species where there's one X ligand above and below and dysprosium in the middle. If you basically deform that geometry computationally and then try to predict a barrier, the more linear it becomes, the molecule, the barrier increases, but eventually that effect starts to level off, and there basically becomes an angle beyond which, as you get closer to 180, the barrier doesn't change very much at all. So you probably don't need something to be perfectly linear to get a very high barrier, which actually, potentially in the case of our systems, pushes you towards the idea that it may well be optimized with our molecules. It may not be possible to go much further with the barrier. Very good question.
In case of like you have the molecules with the two C5 cyclopentadiene ring, then you can define easily the angle between two. But for the more complicated molecules, how can you define the angle there? Because I don't see you put some angle in this several later slides.
Yes, I think we didn't bother with that one primarily because so maybe you were talking about, is it sort of this one here, for example? So the reason we didn't bother putting the angle in for this one is that there's already an equatorial ligand present for this one. So the simple presence of this, it basically negates the significance. For this one, however, it would be much more significant. But as I said, we haven't yet been able to isolate this one, unfortunately. In terms of actually making a system with you know, like deliberately changing the angle. It is interesting in these compounds, because the standard chemical way of doing this, if you make these, you know, these sort of organic matter on the edge of the molecule, if you make it bigger and bigger, this is the standard way of trying to make these things more linear. That does actually work, but the flip side of that is that the bigger you make these groups, eventually it starts to push the whole thing away from the metal. So you do get a more axial molecule, but the strength of the crystal field diminishes. So you're trying to find, if you like a Goldilocks combination that is just right. So it's quite subtle, actually.
I see. Oh yeah. And also when you talk about the spin photon transition induced in the molecular vibration, so you said like you obtain the ring, all the ring is a vibration in plane. But I wonder, like I'm curious whether we can the lanthanum atom also can be in the vibration mode in the vertical direction or not, because in the simulation or in the model you saw the lanthanum atom is just fixed and the ring is vibration.
So the short answer is that it has to be involved in those vibrations. That you are right in saying that, but I think with systems of this type, where the energy gaps between the various Kramer's doublets are sufficiently large that any displacement involving the lanthanides are not significant. Actually, they don't come anywhere near to sort of, if you like, the resonance conditions for the relaxation. So I think if you tried to observe those using some form of vibrational spectroscopy, you would need a non-conventional technique. The sorts of things that we're interested in here are the sorts of things that would come in what we call the fingerprint region, so a few hundred wave numbers, which is basically the organic stuff, the stronger covalent bonds.
I see. Thank you.
Thank you.
All right. Anyone with other questions?
I have another one, if I may. Richard, what about the nuclear spin? So this dysprosium, if I remember correctly, has different isotopes, and normally the nuclear spin plays an important role, especially for the quantum tunneling. So what about nuclear spin?
Yeah, so this is, I should have some factual knowledge at my fingertips here, but it seems to have left me briefly. So yeah, dysprosium has something like, is it 7 naturally occurring isotopes, and a few of them are spin active. But I think their overall contribution in terms of percentage amounts is not as significant for dysprosium as it would be for something like holmium, where of course the spin active nucleus is 100% naturally abundant. So what we have not done, but what other people have done, is the isotopic enrichment here as well. Okay, and I think what they've found is in some cases it can play a role in opening up tunneling pathways, and in some cases it doesn't. We don't see any evidence for that. As to why we don't see any evidence for that, I don't know, because it's been done particularly clearly by people like Wolfgang Bernsdorfer, who I'm sure you know very well. Some really beautiful physics there as well. So it doesn't seem to play a role in the relaxation in these systems. Maybe because the spin active nuclei are not very abundant in the naturally occurring system.
Thank you.
Yeah. Anyone with other questions? Because otherwise I have another question myself, and it's more about if we wish to put some things like the molecule you are synthesizing, but maybe not the very same one, but similar one on a surface. How could we do that? I mean, if you want to make a common experiment, how could we envision a path for that?
Yeah, it's a good idea. So we did briefly try this with a chap in Constance, Michael Phonon. Do you know him?
Yeah, sure.
And that collaboration sort of started, then just fizzled out, basically. How it didn't work with the cations. And I think the problem that we had was to get a system that is basically a salt from the injection point onto a surface. It just gave a glorious mess, basically. So there was no uniform deposition, no patterning. It was just a bit of a mess. So what we need, I think, are some compounds that are charge neutral, because if you do vacuum deposition, they would probably be more prone to subliming, or if you use softer deposition methods like the solution phase method, they'd be much more amenable to that. And you wouldn't have to worry what happens to the anion as well as the cation. So yeah, that was, again, pre-pandemic. We just haven't revisited it. So it's something that we would like to definitely get back to. Of course, this does assume one thing, which is that the molecule is, chemically stable on the surface. And I guess one point that didn't come across in my talk is that our compounds are quite air sensitive. So we need to think of a way of getting around that as well, actually. So I guess these sorts of things you're kind of limited by imagination. So if we can think of a way of getting around it, we're always willing to try. So if you have some good ideas, just let me know.
Yeah, well, I guess we can start working in a glove box and loading some cell for either evaporation or maybe electrospray. But then, of course, we have to. We can envision a way to have the evaporator full in the glove box, that we close it in a controlled atmosphere. Is it inert in nitrogen, for example, or do you need argon?
Yeah, it's fine. Yeah, it's fine with that. So you have glove boxes?
Let's say we have one. It's a bit rudimental at the moment, but it's on the way to get a bit more professional in that sense. So
yeah, because a lot of physics colleagues I talk to, the response is, what's a glove box usually? So we have about 7 of these things in the department here. And part of the limitation with the work we were doing with Mikhail is that they didn't have a glove box, so we were kind of just doing it quickly, and it's not satisfactory, quite frankly.
Yeah, you never know when it's quick enough, right? Because
well, I mean, there's a reason why rare earth elements occur naturally bound to oxygen. Yeah. they really like it. So yeah. Our atoms are covered in carbon, so it's a hard, soft, acid base question. It's just, yeah.
Let's say, to make a long story short, on the chemistry side, we need something neutral, and from the physical side, we need a glove box and a way to put things on the surface, and then we can try to.
We get criticized because the best single molecule magnets are organometallic at the moment, and they're all air sensitive. So the question is, do you just stop working on them for that basis, or do you find ways of protecting them? So one of the things we're working on right now, I just had a new postdoc started, is that we're looking at putting them inside nanotubes and inside metal organic frameworks. And another thing we're going to look at as well is trying to embed them in polymer matrices as well. So if you pick a polymer that is sufficiently impermeable to oxygen, then not only does it protect the molecule from the environment, you can also then process the molecule as a polymer. So there are ways of doing this, I think. And also, actually, when you put things inside a nanotube or a MOF or in a polymer, your periodic lattice vibrations have gone. The spin phonon coupling is fundamentally different. And what that would mean, I don't really know, but there's some interesting work to be done there, I think.
Yeah, I totally follow. We are doing something similar also with the atoms. We're trying to move also from something which is completely on the surface, something which can be a little bit embedded in the surface, and just for the same reason, to protect them a bit more.
I think the soft matter approach, which maybe is not so much your line of inquiry, but if we can somehow build SMMs into soft matter, they do have phonons, of course, but the way in which they disperse is different to a crystalline lattice, and the physics will be different. I don't know how, but it will be.
Yeah, it's sure an interesting direction to explore, right? Yeah. Anyway, so there's room for some last question if you have. Otherwise, we can let Richard go and continue with his day.
Yeah, I have 2 more lectures to give today to the undergraduates.
Yeah, exactly.
I need to rest my voice.
All right, so if there are no more questions, let's thank Richard again for the great talk and the answer to all our questions. And yeah, he will also be invited speaker in the conference in Jeju in the IECMD. So we organize a satellite session. He will be, let's say, the last invited speaker of the session in a time zone which should be comfortable enough for UK, hopefully. And then if somebody will attend the conference, you will have the possibility to meet him again online, unfortunately, because traveling is a bit complicated. But let's hope that next year will bring more opportunity to face-to-face meeting. And
you never know. Yeah, stranger things have happened.
Exactly. All right, Richard, thanks a lot.
Thank
Have
you.
a great day.
Thank you, everybody.